and now I will go and to help you guys to solve some of get you prepared with topic test 5. I'll go through as much problems as possible. All right. Okay, so let's see. I have your rankings over here. I'll prioritize test 5 things first. All right. Question 20. Here, it's about the velocity selector. So this is about a velocity selector, and part A says sketch the free body diagram for a charge when it goes inside, right? So let's sketch out what this is. So you have a positive plate here, you have a negative plate here, and you have magnetic fields going into the page like this. And what charge is this? This guy is a positive charge. So you have a positive charge. So when it is in the middle of the plate, right, when it's between the plates, what are the forces? So you want to draw a free body diagram on it. First of all, is it in contact with anything? No. All right, so you don't have any contact forces. All right, so you just need to look at non-contact forces. And the only ones you've learned, this is question 20, is gravity, electric force, and magnetic force, right? Fg, Fe, Fb. Do you have gravity? Yes, but it tells you to ignore it. Good, so you just need to worry about electric and magnetic. So which way are the electric fields going? The electric field is going downwards, right? From positive to negative. So the electric force will point down. And then magnetic force is going into the field and it's moving this way. So you can use, I think the quickest is your left-hand rule. So imagine the current is now going this way. So your middle finger or second finger will go going to the right, and then the field is going into the page. Which way is the force pointing? It's pointing upwards. Okay. That's it. That's the free body diagram. All right. That will probably be 2 points, or maybe 1 point. I don't know, probably 2 points, one for each. And then part B, state the magnitude of each respective force. Well, the magnitude of this is QVB. Technically, we need to look at the angle between V and B as well. So it's sine included angle. But the angle between V, because it's V cross B, right? So just in case you don't know where this comes from, this creates a vector. So the magnitude of the result of this vector is V sine theta. Theta is the included angle. So the V is going this way, the field is going into the page, so they're 90 degrees of each other. So this is 90 degrees, so the whole thing is just 1. Right? So that is the magnitude of the B force, and this is the magnitude of the E force. It says in term, oh, maybe I should specify in terms of E and B. Yeah, I put it in the third part, but not in the second part. Okay, what is the requirement on the speed in terms of E and B? Should it go through slit 2? So if it needs to be able to go through slit 2, it needs to be able to travel in a straight line, which means there should be no net force going either up or down. So this must be balancing this, and I've derived this in class already. So what you need is you need the magnitude of FB to equals to the magnitude of FE. So you need this, right? And that means you need V to be to equals to the velocity to be exactly the ratio of the field strength, the electric field strength with the magnetic field strength. You don't need these 2 steps to derive it to get the full points. I will probably write it because unless you memorize this out of memory, but otherwise this is how you will answer the problem. I won't commit this to memory, honestly, because it's hard to remember which one's on top, which one's on the bottom. And then part B, it says, if the charge have a speed larger than, notice this is a bit tricky, flip it around, larger than the value B over E, what will happen? Well, so if V is larger than B over, has a value larger than B over E, then that is a typo, I think. Yeah, it should be E over B. Sorry, maybe that's why it confuses people. Sorry, that's a typo. Yeah, it should be asking for E over B. Yeah, right, I'll change that, thanks. So if it's larger than E over B, that means what? That means, well, that means if V is equals to E over B, then you see that these 2 magnitudes are the same, right? Because let's say V is E over B, right? So you'll see that the magnitude of this guy is QE, the magnitude of this guy is QE, so there's no net force. But if it's larger than it, then it means that this will be larger because this depends on velocity. So you have upward force, and this guy will bend upwards, and the reverse is, will make it bend downwards. Okay. Any questions? Yes. Oh, good. Okay, so what if it's negative? Then you need to reanalyze this. So positive plate, negative plate. So negative go in here. Let's look at the electric force first. Which way will it go? The electric force will be pointing up this time, right? Fe, we're pointing up. You can either think of just intuitively, right? Negative will repel and attract to the positive, or you can think of the field lines are going down and negative charges go against the field line, so it will go up. The magnetic force is going to be this time, again, you can use your Fleming's left-hand rule, but this time point your current against its actual velocity, because if a negative charge is flowing this way, it's equivalent to a positive charge going the other way, basically. So the current will be pointing the other way, the field lines go down, so the field line goes in, so your thumb is now pointing down. So the magnetic force is pointing this way. Yeah. Sorry. Yeah. So that's your free body diagram. The magnitudes are the same. This is QVB. Okay. If you want to emphasize that, you should plug in the positive value here, because I'm looking for the magnitude, right? So you can put an absolute value here if you want. And same thing for this. So the absolute value only apply to the Q, actually, because I've already taken care of the direct. Remember, we've just done the hard work of using our rules or whatever intuition to determine which way it's going. When you're looking at arrows in 3 dimensions, then there is no, when you look at arrows in 3 dimensions, there's no sense of positive vectors in 3 dimensions. You can't say a vector is positive. That doesn't make any sense. Just want to dispel this misconception once and for all, because let's say I have a vector F, and vectors have components, right? Let's say it's +3, -5. Tell me, is this vector positive or negative? That's a invalid question. That's a meaningless question. Well, the first component, the fx component is positive, the fy component is negative. So what do you mean? There's no positive or negative. If you ask me the magnitude, well, the magnitude is 3 squared plus -5 squared square root. This is always positive. So what do you mean? There's no sense of vectors being positive or negative. Or the component can be positive or negative, but right. So the magnitude is always positive. The direction, you need to use description words like up, down, left, right, into, or out of the page. Right? These are the words to describe it. All right. There's a question asked, does the magnetic field always opposes the electric force? The magnetic force always opposes, not necessary. In this case, it made it so, but you could get a question with the plates flipped and also the field going the same way. This is a good exercise for yourself, right? Trying to analyze, let's start with a positive, which is easier. Try to do this yourself, right? So try to draw a free body diagram like this. You can create variations yourself on the test. So if it's moving this way, so this is the velocity, this time I'll do this quickly. Which way is the electric force? Well, the electric force is going to go this way. Remember, free body diagrams always start with drawing it from the center of mass of the object. And then the magnetic force is, this is the same as the first case, but just to double check, the current go this way, field goes in, so the magnetic force this time goes up. So you actually have a net force going up, but this doesn't work as, so this is a completely legitimate question, short answer question. It's completely legitimate, but it's not a practical application, because now you will get a net force, right? So your F net is FB plus FE in the upwards direction. So you always bend the particle upwards. So it's not doing a good job in selecting the velocity out of it. So it doesn't work as a velocity selector. It might work in other applications, by the way. Yeah, so it's completely possible. If probably you won't get one, but if you do get gravity as well, if you do need to, probably, in this test or exam, we're not going to include gravity, but if you do, it's not a difficult problem. You just add that up, right? So the net force in this case is, in the upwards direction, is QVB plus QE, magnitude of that, plus mg, like that. So this is the total, minus, because the gravitational force is pointing down. So in principle, if you get an advanced question, right, you can ask what's the net force in newtons, and I give you the charge, I give you the mass, I give you the velocity, and I give you the E and B fields, and you can just plug this in, and you can get however many newton is the net force. I can ask you how much acceleration it is, which is so you can find out what the acceleration is, etc., right, like that. But you won't get all three together. If D is a positive charge, what was the answer? For D on the positive charge, what was the answer? So if it's, yeah, I think I answered that. If it's larger, yeah, it will bend up. I also had this already solved in a lecture, so you can review that. I think this is also discussed in lecture 17. Right, next problem. Question 11. Oh, good. This is a good question. So it's about sketching magnetic field lines. So we have talked about explicitly in class about a single wire. But now let's have two together. How would they look like? So first, for a single wire going out of into the page like this, the magnetic field is like this. Right? And then which way is you put your thumb in along the direction of current, and then they'll tell you, okay, so the B field is going this way. All right, so now what if I have two? So I mean, if they're independent, that's fine. But now you kind of want to put them together. So you need to have them interacting and see, remember like a dipole in electricity, there's a positive and a negative charge for electric fields. You don't just draw them separately like this, right? You need to also draw the combined effect after that. So at least draw 3 lines. Usually it's a reference. So this is how that would look. All right, so how would this look? The idea is, as you can see, it's like joining the dots. Just like here, you're joining up, you first draw them locally next to it, and then try to join them up. So this is similar. Imagine you're drawing it from here, then it will look like this. Okay. And this line would get connected here. This line would get connected here. I'll redraw this, don't worry. So very close to here, it will go like a circle, nothing's changed. Very close to here, it's gonna go like a circle. But in the middle, as it tries to go here, right, if you think of it as a vector, this vector is trying to point down, but this guy is trying to have a vector that's gonna point up, so it's gonna push this up a little bit. But I think the easier way is just to think of connecting the lines together like this. I might have a better picture for you. Yeah, there we go, like this. Okay, so you see here, the direction should be going clockwise overall, like this. So when you see it's very close to it, it's basically a circle, because when it's very close to it, which one is stronger? This one is going to be stronger. So it's basically, this guy's effect is going to be very weak. You can't see it. This is a good diagram. They actually skew it a little bit, but I mean, when we're grading, we won't be that picky. But yeah, so it's skewed a little bit. So it's a little bit flat. You see, it's like an oval. But if you're very close, it's basically a circle. As you go further out, then you'll need to sort of connect the dots. This guy's going clockwise because mine is into the page and this one's out of the page. So use your right hand rule, you'll see that they go like this. Now, if they're opposite directions, then you can try to build this up. So one of them is trying to go this way, nope, the other way, this way. And this guy's going out of the page, so it's trying to go this way, right? So you basically have like an asymptote over here, and I think it's you'll see that at first it will look like a circle, and then here, when it goes over here, it'll try to get squashed in here. So that's the main idea, that they won't cross through each other. Yeah, they're doing a better job at looking through here. So in the middle, let's explain why in the middle it's a straight line. In the middle over here, let's pick a point, this point. The magnetic field due to this guy is going to be pointing this way. So the field due to number 1 is going to be pointing this way. Now the field due to number 2 is also going to point this way, right, at this point. Okay. So the net effect, B1 plus B2 in this direction, is going to be a big vector pointing this way. Right? So in the middle, you have a field line that is basically going straight down. And let's pick another point over here. What is the effect on the green to here? Well, it's going to point this way. That's B due to wire number 1. And B due to wire number 2 is also going to point this way, but it's going to be a smaller arrow, like that, okay? Because it's further away from 2, from 2 over here. So the effect on, this green arrow should be longer than this green arrow, if I'm being precise, but since it just asks you to sketch the pattern, you don't have to draw these arrows, so I'm just explaining why it is the way it is. And so the net effect is going to be something like this. And so everything, if you analyze them point by point, that's how you can build this up. So over here, B1 is going to be pointing this way, and B2 is going to be, use your right hand to wrap it over here. It's going to be pointing this way, but at a smaller angle, because a smaller length, because it's further away than B1 is to the source. So this is B2. And so the net effect would be something like this. So if it is completely a circle, then like if there's no B2, you'll see that this should be, the green should just make a circle, a perfect circle. But because of the presence of wire number 2 over here, it's going to bend it. Do you see the blue? It's a net effect between here. It's going to bend it a little bit towards this side. I should make the blue a little bit longer. Hopefully you understand the point. Right. The presence of B2 is going to make it, the net effect, a little bit tilted. So it's not going to be a perfect circle, but it's going to be squashed, right? If it follows the green, if I just completely follow the green and connect the dots with connect all the arrows of the green, it will be a perfect circle. But because of the orange, it's going to be squashed like this. Let's look at the picture again. So you can see that's why it's not a perfect circle, but it's squashed closer and closer over here. Okay. And then getting the direction right is just using your hand rules, like whether it's clockwise or counterclockwise. All right, good. Any questions about this? Question 26, someone asked. Let me look at this first. I'll get a few of these with higher votes first, and then I'll get to 26. But yeah, thanks for suggesting. So the next question is question 30. Any follow-up with this one, question 11? There's 5 people voted on this. The next one, there's 3 people voted on question 31. Okay. Let me know if you have follow-up questions. Good, this is a Lenz law. All right, so let me just mark this. This is question 11. Question 31. All right, so determine the direction of the induced current on each case. Very good. Okay, so let's start with A. We have a loop, and then we have a current going here, and the current is increasing. Okay, the question is, so this is an external current. Let's label it. And the current is, the question is the induced current, which way is it going, right? Okay. So at first, I need to know the flux that goes through here. So the flux is B times A, right? B dot A. So what is the B field that goes through here? Well, there's a current going through here. So use your right hand and you'll see that basically there's a magnetic field going in here. And this magnetic field is due to the external current. This is B external. It's due to this. It's this guy creating this B field. So on this side, actually, by the way, on this side, it's going to be like this, right? If you wrap your fingers around, you should be able to see that here the B field is going in, and here the B field is going out. It's going to wrap around the wire like this. Okay, but we're just focusing on here because we care about the induced current on this side. And also, by the way, the strength of the B field is going to be weaker and weaker the further you go out, right? It's going to be stronger here, according to the formula of, the question didn't ask, but it's according to this formula, right? So if the further the distance away, this is the distance, perpendicular distance away from the wire, the smaller the B field, the weaker the B field. So this point, the B field is going to be weaker than this point, right? This arrow is going to be shorter than this arrow, but it doesn't matter. The idea is this is increasing. So what happens to the flux, increasing or decreasing? You can tell me. The flux through here, increasing or decreasing? So we can write out a few steps. Right? So I external increases, which means the flux, anyone? Right, so the B will increase, the B external will increase, which means the flux will increase, right? It's B times A, right? If the flux increase, which way does it increase? It increases into the page, right? The wire doesn't want that. It wants to stay the way it is. So it's going to try to create a B field that opposes that increase. So it wants to create an induced B field. Let me use yellow. It will generate its own B field to refuse being increased. Okay, so the B induced will increase out of the page. This is B induced. Okay, which way does the induced current has to flow in order to generate this? Anyone tell me? Clockwise or counterclockwise? Very good, counterclockwise. So the induced current must, so final step, induced current must be counterclockwise. in order to achieve the goal of the yellow B field, the induced B field being that way. Okay? So these are the steps in your head you should go through to answer that. How do we know B field on top half is into the page and bottom is out of the page? Just to save time, if someone can answer that for me, that would be great. I want to do a decreasing example as well. Let's do C. What do you think about C? If I is constant, very good. So if I is constant, then the field is constant. Yeah, let me write it on screen. So part C, if I is constant, then the B field is constant. That means the flux is constant. That means dB dt is 0, right? This guy does not change with time, right? If it's constant, that means there's no induced EMF. That means there's no induced current. Notice you can't calculate the magnitude. In order to calculate the magnitude, they will also need to tell you how much resistance the wire has, because Faraday's law only tell you even if you know how much B is increasing, right? If you can actually calculate, if you can find the formula as this as a function of time, you can take the derivative. You will still only get the induced EMF. You need because current, remember, I repeat this many times, current is the most dependent on what you put in your circuit. So it depends on what the resistance of the net circuit is, and then you can finally determine that. Okay, let's do a decreasing example. What do you think? Let me change part D to decreasing. Shall we do that? Yeah, let's do that. So I'll change part D to decreasing, so that this time the wire is pointing in a different way as well, so to give you some variety. All right, so first let's determine the B field. At this time I'll go through the same 5 steps, just quicker, right? So this way it's going in. Let's make the wire going down again. So again, it's a little bit different. Give you some variety. So the wire going down, right? So here it's going out of the field. Okay, I won't draw too much. But the blue is external, right? It's due to, so make sure you differentiate what's external, what's internal. Okay, so this guy is decreasing. Okay. So B prime, it's a modification of part D, decreasing, in case anyone reads these notes later. Okay, so the B external is decreasing in strength. In which way? What's the direction? So the magnitude of B is decreasing in a way that is out of the page. I always have trouble imagining in and out with these symbols. I always have to think of the arrow. So once I determine it, sometimes I like to put a bracket and just put a note over here like this. So like actually put in the English word, so it's easy to, instead of looking at a symbol, I always get confused. All right, so it's decreasing in the direction that is out. So this, remember, this is the strength. We're talking about the strength is decreasing. The direction is still pointing out, all right? So differentiate that. Okay. So what's the flux through it? So same idea, right? This flux is going to be decreasing in strength. Also the direction, well, I guess the direction of the field is outwards, but technically this is a scalar, it doesn't have direction, but you can imagine it that way. The idea is now I need to create, I'll change it to yellow, right? I need to induce something to refuse this change. So think of, you put your finger sort of coming out of the screen, and it is decreasing. So the wire doesn't like it. So what should it do? It should create a B field to increase the strength coming out. Okay. So it must do this because it doesn't like the fact that it's decreasing. Right? It wants to maintain the status quo. Lenz's law is basically about inertia. It's want to stay the same, inertia. Okay. So we want to induce a B field going out like that. Okay. So B induced must be going out. Right? Can you tell me which way must the current flow in order to achieve this? So B induced must increase going out. So the I induced must be counterclockwise. Let me check. Yes, very good. So it must be counterclockwise. Okay. So these are sort of the 5 steps you go through. All right. Any questions with this as I move on? Okay. Question 16. Let me write out our plan since we're close to the ending time now. So question 16 has 2 votes. Maybe I will do that. And then the next one is question 18. I'm focusing on practice test 5 ones. Again, there's 2 votes on that for 18. And then 25, this one doesn't have a label. I don't know which practice test you're talking about, but maybe I think it's 5. There's also 2 votes on that. And then there's a test 4, I'll skip that. And then question 21, there's 1 vote. And 20, did I go through 20 already? That I did. 20. Yeah, 20 was done. I think that's a redundant one. And then 15, 11, that's done. Okay, looks like that's it. All right. All right, so you know what? I'll keep on and I'll try to go quicker. 31 was suggested earlier, right? Just to make sure. Try to go through this as quick as possible. Not 31, sorry. 26 was suggested. And I'll go through them and keep them in the recording, right? But you feel free to leave. If you do have to leave, thank you very much and hope you have a great night. Okay. 24, yeah, sure, why not? All right, I have to sleep at some time, by the way, but I'll go through some of these. Right. All right, 16. Okay, yeah, this is good. Right, this should be pretty simple. So 16, you have a plane with the fields. I don't like them marking it as a cross, as a plus sign. I'll change it into crosses. But you have a proton going through, right? Proton is for positive charge. All right, so this is purely a test of using Fleming's left-hand rule or the cross product right-hand rule. Right. So this is going, let's see if there's anything else. Sorry, experience of force, yeah. All right, so proton, so current, so imagine the currents going through this way. So remember left hand, so this is Fleming's left-hand rule. This stands for current, this stands for field, and this stands for force. Okay. So the field goes into the page. So put your index finger into the page, right? First finger into the page. Current is going to the left. So anyone in the chat, what do you get? What is the force once this guy is in the field? I get pointing down. Okay. Yep, I will post the slide as soon as the lecture ends and also the recording as soon as Zoom gives me the link. I know in the extra lecture slide, I've made some variants on this. Yeah, I actually put it here. Is there a particular variant you want me to do? Variation D. Okay, good. Thank you. If the proton is going into, oh, okay, gotcha. Yeah, so if the proton is going, what color should I use? I use just white. If the proton is going into the page as well, it's a little bit hard to draw now. So let me draw this as the proton, and then I'll say this is the velocity that's going into the page. Now they are parallel to the field, so the force would be 0. So it doesn't experience any force if it goes parallel to the field. How do we see that? Remember, go back to the definition. If this is, there's several ways to know, to see this. You can look at the magnitude of that. So the magnitude of Q times the magnitude of B cross B. All right, let me actually do the steps in case you've never seen this before. So the rules is in math. If you have a magnitude of everything, you can break it down into the magnitude of something and then the other thing. So this is, B cross B is one scalar, sorry, one vector, right? So you cannot put it in each, okay? Because this itself produces a vector. So you need to keep these together. But this is a scalar multiplied by it, so you can actually split it up like this, all right? So fortunately, this is the charge is a proton, all right? So the magnitude of it is just itself, but just in case it's an electron, I'll keep the absolute value sign like this, right? So this is the magnitude, right? So what's the magnitude of that? It's VB sine theta included, right? So if V and B are parallel, the included angle is going to be 0, right? So that's why sine 0 is 0, and you'll get a big fat 0 like this. So whether this is an electron or a proton, it doesn't matter. It only experiences magnetic force if V is not parallel to B or anti-parallel to B. So if V is at an angle to B, actually the theory is you should split the V into its parallel component and its perpendicular component. And only the perpendicular component is going to contribute to a force. Let's say in this diagram, which way would the force point? So let me use the right-hand cross product rule this time. So you put your palm you point your fingers towards B first. In this case, it's at an angle, and try to wrap your hand towards B. But if you put your hand like slap on your screen like this, you'll break your hand if you try to wrap it backwards. So the only way is you flip your thumb back towards the screen, and now you can actually have a chance to wrap your hand from B to B, or right hand from B to B like that, right? So and you know that the force must always be perpendicular to both of the inputs. Right? So this is a feature of cross products. The output is always perpendicular to both of the inputs. So as a result, if the input V and B lies on the screen, there's only two options for F. It either comes out or in, okay? So your thumb will either point out of the screen or into the screen. Just see which way does it make your right hand easier to wrap from V to B. All right. So from V to B, it's going in. So the force is going to be pointing into the page. So the force is going to point into the page, right? And if this is the included angle, you see that this part contributes to it, right? So it's the magnitude of V times sine theta, right? So this length is this. So that's why this is the part. V sine theta is the perpendicular part that contributes to the magnetic force. And that's why this is a good use of cross products. Okay, any questions? Good, all right. Yeah, it's not a multiple choice option, sorry. Next, question 18. All right, I think I'll be able to do it quickly since the answer is there already. So again, Fleming's left-hand rule. What is it asking? It's determining the direction of the current. Good. Okay, this time it's sort of reverse engineering. It tells you, so use this. I'll just keep it here. Use this, but you're given the force. Usually we find the force last. You're giving the other two, but this time it asks you to find the current. So point your force upwards, and then the field from right to left, right? And then your middle finger should be pointing sort of inside into the page that way. Any questions for this? All right. Next, question 25. This is another good one. So you have straight wires pointing out to distance d apart, right? So let's sketch that out first. Question 25. So you have a wire here, you have a wire here. Let's call them I1 and I2. Actually, they both have the same current, but I'm going to draw magnetic field vector, so I want to differentiate which is 1, which is 2. Then you have 3 points here, each of them is d/4, right? The whole thing is distance d apart. All right, location, all right, that's a bad idea. I'll call the locations 1, 2, 3. I'll call the currents A and B. All right. So you want to find the net magnetic field, magnitude and direction at each of the points. Let's do number 1 first. All right, so due to wire number 1, again, dot means coming out, right? So let me make my life slightly easier, out of the page. So due to wire A, it's going to produce a field going this way. Due to wire B, it's going to produce a field going, use your right hand again, right? At point number 1, it's going to produce a field going this way. Now, which arrow should be longer? Should arrow A be longer or B be longer? Good, A should be longer. Okay, this is B due to wire B. Okay, so yeah, so the net, and then we have a rule, right? We have the formula for this, right? And so the B net is going to, we know it's going to be to the right because of the magnetic field due to wire A is going to be stronger. So this is going to win. So let's make it BA minus BB. All right, so mu naught 2 pi is common. I'll skip a few steps. So I just need the current A over the distance A minus the current B over the distance B. Actually, the currents are the same, so let me pull that out as well. So it's just 1 over distance from A. If I have time, I'll color code this, but that's fine. And the distance from B. So what is the distance from A? Well, it's d/4. What's the distance from B to point 1? That is 3d/4. Okay, and then the rest is algebra, as they say. So let me, I hate 3-level fractions, so let's flip this up. So it's 4 over d minus 4 over 3d. How do I do this? Let's multiply a 3 and a 3, right? So now I have a common factor over here. So I have mu naught I over 2 pi. 3d is a common factor. On top, I have 3 times 4 minus 4. So just 2 times 4, right? So that's 8. Okay. And that's the result. If you like, you can clean up this a little bit. 4 mu naught I over 3 pi. Did I get it right? 4 mu naught I over 3 pi d, sorry. Yes, forgot about the d. And direction is to the right, magnitude here. I think you can understand the last one, and let me, yeah, Any follow-up questions? For two, they're equal distance. So even without doing the math, I know that the strength will be equal because they have equal distance away and the current is the same, right? So they'll just balance into zero like that at point number 2. Any follow-up questions with this? Okay. I'll give 5 seconds before I move on. Okay, no, all right, 21. Okay, is there a particular variation you want me to do? Top left, top right, bottom left, or bottom right, while I write out the question? It's asking for the magnetic force felt by one of these particles, or do you want me to do more than one? Let me know. So this is the current, bottom left, all right, good. So this is the velocity. So first, I want to find the magnetic force. If you are unsure, write out the formula first. Okay, so that I want the magnetic force on a particle, you use this formula. If you want the magnetic force on a wire, on a particle, right? Particle on a particle Q, on a charge Q. If you want it on a wire, use this. Okay, so this time I need to use this. Okay, this is appropriate here. So what do I need? I need the charge, I need the velocity, and I need the B field. So let's do one at a time. I have the velocity, good, done. That's 1/3 done. I need the B. So what B here is the external B field that this guy is experiencing. It's whether the wire experiences or the particle experience. So the B field here is due to the extra current that's moving here. So the current generates a B field around it. And this guy will have a B field going into the page, right? On this side, if you wrap your right hand around it. So the B is going into the page. Now do a cross product. Let's use our right hand. Do a cross product with V cross B. So V is pointing to the left of the screen. So put your right hand pointing to the left of the screen and try to wrap your hand. So B is, I hate the cross notation. So this is into the page, right? So wrap your hand into the page after pointing to the left, all right? So it looks like the easiest way is that way when you have the force, when you have the result of V cross B pointing down, okay? All right, so V cross B is pointing down, but that's not the final answer. As you see, there is a Q over here, right? So let's differentiate this clearly. So V, notice I'm not writing F, I'm writing V cross B is pointing down. But the vector F is negative some magnitude times this direction. Whenever you have a negative number here, multiplied by a vector, that flips the vector. So if the vector C points this way, negative C is the same vector pointing the opposite direction, right? So what is negative number of this? So FB is proportional to negative of this, which means it has to be pointing up. So this is the direction of F. It might not be the same length, and it shouldn't be actually, because it should be multiplied by Q, right? But you know, we won't be picky about these lengths, but you will potentially have a different length. So this part, the orange is just purely the mathematics of V cross B. Now you have to take into account of the physics that this guy is a negative. Okay, right. Notice this is not looking at the magnitude. I only take absolute values of things if I'm interested in magnitude. If I'm interested in direction, which I am now, then I cannot. Okay. Any other variations or any other follow-up questions on this? Top left, all right, yeah. So the magnetic field, same thing. We're going to use this, right? So top left, let's draw the particle. Let's repeat this. Here, positive, going this way. All right, so I already have V. Now I just need B. So let me change it to blue. So it's going out of the page here. So B is going out. Again, I like to write it out. All right, so good. Let's use our right hand again. So right hand pointing to the right of the screen, and you want to wrap your fingers out of the page, right? V cross B. So which way is V cross B pointing? I'm going to hurt myself unless I twist it this way. So you want to wrap your hands out of the screen. So I got my thumb pointing downwards. So I have V cross B being pointed downwards, and this is a positive charge. Good. That means the F is going to be proportional, not oppositely proportional, but directly proportional to the V cross B direction, like that. You can also use Fleming's left-hand rule, by the way, just to check over here. Fleming's left-hand rule say that you need to point your index fingers in the field, right? So the field is into the page, so point your index finger into the page. How about current? So the charge is moving this way, but it's negative. So the conventional current, right? The conventional current is the flow of positive charge. So think of it going to the right, and now you get your force going up. Your thumb should be going up nicely, right? So that will work. You can double check with this as well. This time the current is just going this way, field is out, and your thumb is going down. Okay. So learn both ways, because Fleming's left-hand rule is good for all the magnetic force stuff, but it doesn't benefit you into 3C or other fields, right? The cross product is, and if you learn both in an exam, you can always double check. So that's good. It'll give you an extra thing, double check. All right, get any follow up here? No, I'll move on. Okay, so 15. So this is there a particular variation you want me to do, A, B, or C, while I write out the problem? And I need to find which direction the wire would move. Okay, direction, which means basically the force on the wire. Part D, okay, good. D is asking flipping both, all right. So we'll flip this, and flip this, north to south. Okay, so I'm doing D. Okay, all right, so force on a wire, this time we use the variation of this, right? Okay, so what is the L vector? L vector is just the direction of the current, so it should go this way. I'm going to use the right-hand cross product rule. And I need a B field, so let's draw the B field is going from north to south. All right, so now let's use our right hand pointing towards the current, so to the right of the screen, and then wrap your hand downwards. I get my thumb pointing into the screen. Okay. So the force is going to be into the screen. Okay. Any questions on that? All right, good. And where are we? 15. Okay, almost there. 26 is good. Okay, so we have 4 wires this time, and we want to find which variation do you want me to do? A or B? I want to find label all the fields from each source. All right, good. Let me know A or B if whoever asked this. B, okay. So we want to find the net field in the middle. Let's call them 1, 2, 3, and 4. Yeah, that's the same as what they called it. Good. All right, so start with one at a time. Let's start with this wire. Cross means, hopefully it's not just me that finds the cross and dot confusing. I always have to think of an arrow. So cross goes into, all right, and then so I'll just label everything first. Into and out of. Okay. All right, so into, again, field due to wire. So the wire is a source which creates a magnetic field. Right, so point yourself in, thumb into along the wire, and that means it's generating field lines like this, right? So these are the field lines due to number 1 with this direction. So at this point, this is the magnetic field, right, at this point due to 1. Okay. And then let's do number 2. And this guy, again, we know that the field lines, magnetic field lines, are going to be circular around the wire. So now what's just left is to find the direction. What's just left to do is to find the direction, whether it's clockwise or counterclockwise. So you can use your rule again. Now you're going to cheat and know that if this guy is clockwise, this guy has to be counterclockwise. But you can verify. Don't trust that too much. Verify with your right hand. But it's a good double check. If one of them is one way, the other has to be the other way. Right. So this guy's going to, at this point, it's going to be tangent to the field lines. Right. So that the relationship between field vectors and magnetic field lines, same as electric field vectors and electric field lines. The lines tells you, the tangent of the line tells you the direction of the vector at that point. Okay, so this is B2. Let's use green for 3. So we'll get field lines like this, right? And the direction of this is out, so it's going this way. So at this point, it's going to point this way. B3, I think you get the idea. And last one with here with the orange, I'm not going to draw all the circles, but this is going into, so it should be pointing this way. And if they are the same magnetic field strength, they will all cancel. So these are currents due to wire, and due to wire source is mu naught I over 2 pi, the distance, perpendicular distance. So since they have the same distance, and this, if they have the same current, which is not, oh, it is specified, they have the same. So the net field here is going to be actually 0. Did they ask? No. Let's just find the direction. Yeah, just the individual one. But in case they ask, they will probably all cancel because B4 cancels B1, B2 cancels B3. Okay, good. Any questions? All right, last one is question 24. All right, good. Any particular variation? I can probably do all 3, but any variation you want me to focus on first? So I have a wire. out here. I have point C, point D somewhere here, point E somewhere here. Right. I'll start with the first one if no one suggests. So again, draw your magnetic field lines around this. You know that they are concentric circles. Right. Around it, like this. All right, it gets weaker and weaker the further you go away. Now, what's just left is the direction. This guy's going out of the page, yes. So with your right hand, you can tell that these magnetic field lines are going this way. Remember, just sometimes put yourself back in the physics of things. What you're really solving is, if you put a compass over here around it, it will point this way. The north-south compass would point this way. So these are what these abstract looking blue lines really mean in real life, okay? All right, so C, this is going to be very easy once you understand this, right? So the B at C is going to point pointing that way. The B at E is good. You just need to draw a tangent to the line. Since E is a little bit lower, right? So it's not, if E is here, it's going to be directly up. But if it's a little lower, just make sure it's a tangent to there. So B at E due to I. Remember, it's always at a point due to a source. Right? This is what fields are. Even for electric fields, it's the same idea. It's always at a point due to whatever source it is. And finally, D is this. Okay, any questions? Due to. All right, thank you so much. Hope this is all good. And I have nothing else to say other than wish you guys all the best. And I hope to see you guys tomorrow as well. Thank you very much. Have a good night. Good luck tomorrow. See you guys tomorrow. Bye.